Hey, welcome back, you guys. Your favorite calculus course. We're going to take a look at some implicit differentiation. The old way to do this first example is we say, well, let me solve for y. Can I solve for y? Sure. Let me go ahead and factor a y out. Let me see if I can isolate y. Now I'm going to go ahead and divide both sides by that x plus 1. And I'm like, oh, good. I can write this y is now in terms of x, right? And so I can run the derivative. So dy dx would be 3 stays there. I go ahead and run the power rule, -1, x plus 1, now it's to the -2. Derivative of the inside, which is just a 1. And so we've got our dy dx ends up being -3 over x plus 1 squared, right? That's called explicit differentiation. That's what we've been doing this whole time. We've been able to have a y, and we have all our x's on the right-hand side, and we've been able to take the derivative, right? Now, sometimes, like if you look at this second example, you can't solve for y. So you've got a problem. See the x cubed minus 2y squared plus y equals 4. There's no way you can get y isolated. There's no way you can get y isolated. So how would you do that? Well, let's do this first one, which is a little simpler, but let's do it with implicit differentiation. So let me go ahead and erase this one. And when I say do this with different implicit differentiation, I just mean let's just go ahead and take the derivative of both sides as is. Now I'm taking the derivative with respect to x. I'm taking the derivative with respect to x. So I've got derivative. So I've got the product rule on this. See, I have x times y. I've got the derivative of the first times y plus the first. Now the derivative of y. So let's think about that for a minute. Derivative of y is dy dx plus derivative with respect to x of y is 1 dy dx. Because again, we don't know what y is. And then over here we've got the derivative of 3, which is just 0. Okay? And so what we end up with here is we've got to take this y over. So I've got x dy dx plus a dy dx, and I'm going to factor out a dy dx. So I have x plus 1 equals negative y over is negative y, sorry. So dy dx, when I go ahead and divide both sides by x plus 1, I got negative y over x plus 1. Now, see, the problem with this is I'm like, okay, I don't know what y is. I am lucky that on this problem, though, I could have solved for y. You know, my xy plus y is 3. Remember how we solved for y? So y was 3 over x plus 1. So I can throw that in right here. So my dy dx does end up being 3 over x plus 1 all over x plus 1. So you see how it does end up being the same. Boy, that was a lot more work than just solving for y and solving, though, right? So the ideal is if I can solve for y and take the derivative, I will. If I can't, like in the next example, I'm just forced to do it with implicit differentiation. So let's look at this. So we're looking at this one here. We've got x cubed minus 2y squared plus y equals 4. Again, we cannot solve for y. So let's go ahead and take the derivative with respect to x on this. And let's run through and talk through that again. So I've got the derivative of x. Derivative with respect to x of x cubed. The variables agree. So I'm going to say, okay, that's 3x squared. Derivative of x with respect to y. So I'm taking this. What would that be? Well, that's negative 4y to the 1 power But chain rule, I don't know what y is, so I just have to say that's dy dx. Again, that's a lot. It's a lot like your, u to the third. If I'm taking that derivative, f of u, then f prime of u would be 3u squared u prime, right? So I've still got to take that derivative. That's the chain rule part right there. That's why I throw on dy dx. So if the variables do not agree, I'm taking the derivative with respect to x, it's not agreeing with what I'm taking the derivative of, I got to throw on my chain rule dy dx there, right? That's the chain rule part. So derivative of negative 2y squared is negative 4y to the 1 dy dx. Again, variables did not agree. Don't forget chain rule. I don't know what y is. Y could be like x to the fifth or something, right? So I got to throw the chain rule on. So I don't know what it is. Now let's go to the next one. Now plus y. Well, the derivative of y is just 1 chain rule dy dx. And then over here I got a derivative of constant, which is 0. Now I'm going to isolate my dy dx. So I've got negative 4y dy dx plus a 1 dy dx. So I want to get dy dx all by itself. So I have negative 4y plus 1, or 1 minus 4y. Over here I've got a negative 3x squared. So see how I can now solve for dy dx by dividing both sides by 1 minus 4y. And so the derivative dy dx ends up being negative 3x squared over 1 minus 4y. Now it'd be nice if I knew what y is, but I don't. There's no way to solve for y, so I just leave it right there. I've just taken the derivative with respect to x. I kind of jumped the gun on this, but this was that very first problem we did, and I showed you how you could take this, even though you could solve for y explicitly, it ends up being the same as if you had done it implicitly. And if you remember, we ended up getting the same thing once we substituted in for y, right? All right, let's go ahead and do it on this one. Notice you cannot solve for y on this, so we're going to go ahead and just take the derivative as is. So we've got x squared y, so I've got to use the product rule. Derivative of x squared is 2x, derivative of the first times the second, plus the first, I leave that x squared alone, and then derivative of y is 1. Variables do not agree, so I've got to throw on chain rule dy dx, because I don't know what y is, right? That's my u prime, if you will. That's the y prime part. Plus, now I'm looking at y squared x, so derivative of the first, variables do not agree, times the second, derivative of the first times the second, plus the first, derivative of x is just 1. Over here I've got derivative constant, which is 0. Now what I'm going to do is I'm going to take over anything that doesn't have a dy dx on it, take that over, take this over, and then I can go ahead and take a dy dx out. I've got x squared plus 2xy, sorry. And so it looks like I've got dy dx is negative 2xy minus y squared over, go ahead and divide both sides by x squared plus 2xy. And if you want, you notice in the top there, I could take a negative y out and I'd have 2x minus y. 2x plus y, sorry. I could take an x out of the bottom here and I'd have x plus 2y, but still nothing factors. So either of those there at the end be fine. All right, here's our next one. We got again. Notice we can't solve for y. No good way to solve for y, so we're just stuck taking its derivative as is. So let's take the derivative with respect to x. both sides here. And so what do we have? Well, we got to run the power rule. 2xy plus 3. Now it's to the first power, but we got to take a derivative of the inside here. So I've got, and I'm going to think about this as 2x times y. So derivative of the first times the second plus the first derivative of y is 1 dy dx. And then plus 0 on that, because derivative of 3, of course, is 0. And then over here on the right-hand side, derivative of the sine of y is the cosine of y. Again, the variables did not agree, so I've got to throw on dy dx on that, right? Y prime, because again, I don't know what y is, so I got to use the chain rule. Y prime right there, dy dx. And so it looks like we got 4xy plus 6 times 2y plus 2x dy dx equals, I'm going to throw that dy dx out front here, cosine y. Okay. So I'm going to have to FOIL this, it looks like. So I got 4xy times 2, I got 8xy squared. And then 4xy plus 2x, I got 8x squared y dy dx. Now the inner term, 6 times 2y, I got 12y. And I got 12x dy dx equals dy dx cosine y. I got to get all my dy dx's on one side. So I'm going to subtract this dy dx cosine y, both sides. So that's gone from there. And then I'm going to take that to the left-hand side, so minus 8xy squared. Take that to the other side, so that'll be gone. I'm going to subtract this 12y to the other side, minus the 12y over here. And so I have, let's see, 8x squared y dy dx plus 12x dy dx minus cosine of y dy dx, or dy dx cosine y, however you want to write that, equals negative 8xy squared minus 12y. Take a dy dx out, so I have 8x squared y plus 12x minus cosine y. And then divide everything by that right there, 8x squared y plus 12x minus cosine y. 8x squared y plus 12x minus cosine y. And that's my dy dx right there. There's my dy dx. Well, looking at this one, again, no way to solve for y, so we're going to have to just go ahead and take its derivative with respect to x here, both sides. So we got derivative of e to the xy, so that would be ln of e. Of course, that's just 1, e to that. And then I do have to do the product rule on that xy. So derivative of x is 1 times the second plus the first derivative of y is 1 dy dx. Plus, now I'm taking the derivative of x squared, which is 2x. And then I'm taking the derivative of that minus y squared, so minus 2y chain rule dy dx. And then over here on the right-hand side, derivative constant, luckily we've just got a 0 right there. Okay. So we've got e to the xy times y plus x dy dx plus 2x minus 2y dy dx equals 0. I'm going to go ahead and distribute that. So I've got y e to the xy plus x e to the xy dy dx plus 2x minus 2y dy dx equals 0. And take that 2x over, take that minus y e to the xy over. And I'm also going to go ahead and take out a dy dx from what I'm left with. So I'm left with x e to the xy. Once I take a dy dx out of both of those, minus 2y. So once I divide both sides by what's in red, I'll have negative 2x minus y e to the xy divided by what's in red there, x e to the xy minus 2y. So notice here they want the first derivative and the second derivative. So let's go ahead and take the first derivative of this x cubed plus y cubed equals 8. Derivative of x cubed is 3x squared. Derivative of y cubed is 3y squared. Don't forget to y dx on that. Variables do not agree equals 0. Subtract 3x squared both sides. And we've got 3y squared dy dx equals negative 3x squared. And go ahead, divide by that 3y squared. And so it looks like our dy dx here ends up being negative 3 over 3 is just a negative x squared over y squared. Okay, here's our first derivative. So let's go ahead and take the second derivative now that we have the first derivative. So the second derivative will be the derivative of the derivative. So the second derivative would be, so I'm going to have to run the quotient rule here. Derivative of the top times the bottom minus the top derivative of the bottom, which would be 2y dy dx. And this is all over bottom squared. So we got the second derivative that ends up being negative 2xy squared plus x squared plus 2x squared y dy dx over y to the fourth. Now you're looking at that dy dx and you're like, oh, that's ugly. Well, we know what that is, so we want to make a substitution for dy dx right there. What is dy dx? That's negative x squared over y squared, so go ahead and throw it in right there. And then I'll have my second derivative. So the second derivative, once I throw in the dy dx, negative 2xy squared plus 2x squared y times dy dx. Again, we know that's negative x squared over y squared because we already found that. And this is all over y to the fourth. So I got negative 2xy squared minus 2x to the fourth y over y squared over y to the fourth. And notice I have a y on top and a y squared on the bottom, so that'll just leave me with a y right here, 1y. And so let me give this over 1, which means I got to give it a y and a y. So now I have the second derivative is negative 2xy to the third minus 2x to the fourth over y to the fourth. So I'll multiply by the reciprocal 1 over y to the fourth. And notice I'll have 1 y to the fifth on the bottom. And there's our second derivative. This last one here is probably my favorite. I love the visuals on these, so we'll give you the visual at the end. But let's go ahead. It says a point 4 zeros on this curve. Find a line that's tangent to the curve at 4, 0, right? In fact, you know what? Let's show the curve right now, and then we'll get into the algebra, and then we'll come back to the curve. So I open up Desmos.com. Notice I can't solve for y, so it'll still graph it. Desmos pretty good about graphing even non-functions, right? So we've got this funky looking curve here, and we're supposed to find the line tangent to the curve at 4, 0. So there's 4, 0, right? We want the line tangent to the curve, so it's going to have like a positive slope going through there. In fact, let me show you it right now. This will end up being what we get. See that line tangent to the curve. So we're going to find the equation of that line. And you know what? I'm going to add to this a little bit. I'm also going to find the equation of the line that is normal to the curve. Now, when I say normal, that means it's perpendicular to the tangent line. If you want to make a note of that, normal to the curve is perpendicular. And so that one would end up being have a slope instead of 3 of being negative 1/3, and then a y-intercept of 4/3. So you can see the line there in purple is the line that is normal to the curve. Okay, so this is what we're doing, but we're going to be doing it algebraically, right? I want to give you the visual of this just so you kind of have that in your head here. So let's go back to the problem now. And we know in order to find, we know the derivative is the slope of the tangent line, right? So we're going to have to find this derivative. So find slope of the tangent by finding dy dx. All right, we got to find dy dx. So let's take this derivative. And so we got derivative of x cubed. We got 3x squared plus 5y to the 4th dy dx equals, now I'm thinking about this as like 4x times y. Derivative of the first times the second plus the first. Derivative of y is 1 dy dx. And then derivative of 64, of course, is 0. And I'm going to get all my dy dx's on one side and everything else that's not to the other side. So I take this minus 4x dy dx to this side, minus 4x dy dx. And so what we have is, once I take a dy dx out, I've got 5y to the 4th minus 4x. And over here I've got 4y minus 3x squared. So let's go ahead and divide by that. 5y to the 4th minus 4x. And so it looks like we've got dy dx here ends up being 4y minus 3x squared over 5y to the 4th minus 4x. Okay, there's our derivative. Now, we wanted the derivative, the slope of the tangent line, we wanted it at what point? It was at the point 4, 0. So here's your notation on that. I'm going to take the derivative. I'm going to find the derivative, in other words, the slope of the tangent line at 4, 0. So see how I put in, so that's my x and my y that's going to go into this. So 4y, my y is 0, minus 3, my x is 4, my y is 0, my x is 4. And so the slope of the tangent at 4, 0 ends up being 0 minus 3 times 16. 3 times 16 is 48. So I got negative 48 over 0 minus 16. Negative 48 over negative 16. The slope of the tangent line there is 3. Okay? And so now I know, I'm like, all right, let me go ahead and come up here. Now I have my slope of the tangent is 3 at 4, 0. So I have a slope, I have a point. I'm going to go ahead and write the equation in point slope form. So y minus 0 equals 3, x minus 4. Go ahead and distribute that. That was the equation of the tangent line at 4, 0. And the last thing I said is, you know what, I wanted to add on to this. What's the equation of the normal line at 4, 0, right? Well, I know the slope of the tangent was 3. So If it's perpendicular, the perpendicular slope would be, 3 over 1. If you remember back from pre-calculus, it would be the opposite reciprocal. So 3 over 1, if I flip that over, that's 1/3, but it was positive, I got to change it. So that will be the slope of the perpendicular line, the normal line. So now I know the perpendicular slope, and I have a point, y minus y1 equals mx minus x1. And I can write the equation of the normal line once I distribute that. So there's my slope of the tangent. There's the slope of the normal line. Let's go back one more time to the graph, and you see there's our 3x minus 12 in green, and then the purple is the normal line. Again, thanks so much for watching. Hope you enjoyed implicit differentiation. See you next time.